And then to share the screen. So before we get into the real chapter, just to show you a few things about pH. So here's a 1 molar solution of hydrochloric acid. So that will give you a pH of 0. Here's a 0.1 molar solution of hydrochloric acid, which give you a pH of 1. So notice that between here and here is a factor of 10, and between here and here is a factor of 1. That's because pH is a logarithm of base 10. So a difference in pH unit of 10, excuse me, a pH unit of 1 represents a 10-fold difference in the concentration of hydronium ion. So your stomach is somewhere between 1 and 3. So your stomach acid is about 0.1 molar hydrochloric acid. And it's a pretty dangerous solution, which is why barf could really be considered a dangerous weapon. So here's lemon juice, pH about 2.3. Vinegar is about pH 3. So wine has organic acids in it. Pickles has acetic acid in it. Carbonic acid, excuse me, carbonated drinks has carbonic acid. Grapes and orange juice are about pH 4. These are all weakly acidic. Beer, again, because of the carbonic acid. Rain, you would think rainwater would be neutral, right? pH 7. But because of all the CO2 in the air, it becomes acidic. So milk is a little bit acidic because of the lactic acid in it. In sour milk, it gets even more lactic acid, so the pH goes down. Eventually, that could cause the protein to precipitate out, so we call that curdling. And of course, pH balanced shampoo is about pH 6, so it's not really balanced, is it? It's more like an advertising thing. Oh, our shampoo is balanced, so you better buy ours. So pure water is 7. Blood is slightly alkaline, about 7.4 because of bicarbonate and because of dihydrogen phosphate. So egg white, seawater, about pH 8. Baking soda, about 9. Soaps, milk of magnesia, about 10. Of course, milk of magnesia is taken to neutralize some of excess stomach acid, which is around here, right? So bleach is acidic, ammonia, excuse me, basic, Drano, and a 1 molar solution of sodium hydroxide gives you a pH of 14. So most people think that pH varies between 1 and 14, but the pH can be even a negative number. pH is simply a logarithmic scale, so whatever number you put in there, it just obeys the mathematics. And here's something interesting. I thought I would apply this to foods. Look at all these acidic foods. Most foods are acidic. And the reason is, say the plant is going to produce a cucumber. Well, what does the plant want to happen to that cucumber? It wants it to produce seeds, and the seeds grow and form new cucumbers. It doesn't want to make it so that bacteria and mold could come along and just chew up everything and there's nothing left, to propagate the plant. Beef is slightly acidic because of lactic acids and carbonic acids. So you get all the way up here and you get fish, slightly acidic because of lactic acid and everything. Then you get tofu, and some types of tea are slightly alkaline. So you can see that almost every food here is acidic, some much more than others. Tofu is the only exceptions, but then again, I don't really consider tofu a food. I don't know about you guys, but to me, the definition of food, it should be something that tastes good. And tofu has no taste. So I really consider it more of like a building material or something. I don't know, some people might like it. So here's just some pH values. So a pH of 7 corresponds to a hydrogen ion concentration of 10 to the -7th. pH 6, you can see one difference in pH unit is a 10-fold difference in concentration of the hydrogen ion. And you know, with this COVID virus, I found out that a couple of people that I know, not closely, I've noticed that on their Facebook sites, they've become anti-vaxxers. What I mean is that, oh, well, all this stuff about the COVID virus is this BS. All we have to do is take vitamins and eat fruit and this and that. And then they start talking about pH this and pH that. And all the pH values are wrong. So I'm trying to point out to them that they don't know what they're talking about. But, you know, people that are anti-vaxxers are essentially like, that's their religion, if you know what I mean. But I found this many years ago. So they use pH to propagate or promote their own agenda. So look at this. Consume freely. Raw is best. So this is a group of people that have hijacked the concept of pH to promote dangerously their own ideas. So they're trying to get people to eat raw food. So anybody know why we cook food? Maybe because it's more sterile, we don't get sick from food poisoning. Maybe because we cook our food because it's easier to digest. We get more nutrients from the food that we eat if it's cooked. And some researchers have gone as far as to say is that's the reason why the humans, when they started cooking their food, were able to extract enough energy from that food to grow our brains as big as they are. That caused us to be able to evolve. And if you look at this high alkaline food, it's like, I'm sorry, these are not alkaline. These are acidic foods, but they don't care. High alkaline ionized water. So here they have most tap water, so that's correct. Now they're getting to the acidic part, so this stuff I could believe. All this stuff up here I do not believe. And then over here, anything that's acidic, you should sparingly consume or never. And then colas, off the chart. So sodas are off their chart. They're not off any other people's chart, simply because of the carbonic acid. And then listen to what it says over here. It takes 20 parts of alkalinity to neutralize 1 part of acidity in the body. That is total bullshit. Well, like we talked about with normality, right? If you got 1 equivalent of acid, how many equivalents of base do you need to neutralize it? 1. Okay, so they're 20 to 1 is this BS. So anyway, just to give you an idea. I had a student one time, used to go to the farmer's market, and she was telling me the story about this old lady that she would see there all the time. And she would carry a pendulum in her hand. So she would go up to a hand of bananas. And so she's going like this with the pendulum. And then she's moving the pendulum all over the different kinds of bananas until she sees one that she likes. So when the time she was going like this, like maybe clockwise, by the time she got to the banana she liked, her hand was going the other way, counterclockwise. And so she asked the old lady, "What are you doing?" "Oh, I'm measuring the pH." It's like, well, that's pretty interesting. So this figure 3, here we have some really, really strong acids. Nitric acid, sulfuric acids are very, very strong acids. Look at their pKa's. These are negative numbers. Then here's HI. If you give off its H, because that's what it wants to do because it's a strong acid, now it gets just the I minus. So here's the psychology I want you to kind of understand. Why is this a strong acid? It's because it really, really, really wants to get rid of its H plus. When it does that, it becomes more stable. Once it gets rid of its H plus, because it wants to get rid of it so badly, what is the likelihood that it's going to act like a base and take one back? Not very likely. So what that means is that a strong acid will turn into a weak base. If you go to the other end, here's ethanol. Ethanol is not acidic. You put ethanol in water, it doesn't change the pH at all. So here's the hydrogen that could be made to be acidic. But this is an extremely weak acid. But what if you forcefully take off that hydrogen ion right there, and now you make it into a base? Well, that's now going to become an extremely strong base. So if you have a weak acid, its base is going to be very strong. But most things are in the middle over here. So we just say it's moderate. So if you take something like acetic acid, it's a weak acid or a moderate acid. So if it gives up its H plus, it's just as happy to take it back again. So any questions about that? Now, get into the actual chapter. So just some definitions and some properties. So acidic solutions taste sour. Basic solutions taste bitter. So do you think that has anything to do with food? Yeah, very much so. And I was really fortunate many years ago. This colleague of mine retired a couple of years ago, but he was a chef, local boy from Kauai, so we got along really well. And he had gone all over the world, opening up really high-level restaurants for different hotels and stuff like that. He ended up being a teacher at culinary arts at KCC. He ended up taking my classes. He took my Biochem 141 and the Biochem 244. And then I used to give lectures to his students and everything. And it was really interesting how he turned this whole concept into a way to teach his students how to be much better chefs by actually using chemistry. So then they invented this dye called litmus. So litmus is a dye that you extract from a plant. If you put it into an acidic solution, it turns red. If you put it into a basic solution, it turns blue. So maybe you've heard about the litmus test, right? And so the reason why this was made is because it was something that was more experimentally valid than just tasting. So you can imagine if somebody said, you're working in the lab and you're the new kid in the lab and somebody says, hey, I wonder if urine is acidic or basic. And somebody said, well, let's use litmus paper instead. Does anybody know how they first discovered that diabetes had to do with glucose in the urine? Yep, somebody in the old days tasted the urine. So the pH meter was not invented until 1934. So acidic solutions neutralize base because of this reaction right here. Basic solutions neutralize acid. So go back to the sessions that we covered on acid-base and neutralization reactions, and this is simply a review of that. Acids will produce CO2 from calcium carbonate and calcium hydrogen carbonate. Here's what happens. The CO2 gets solidified. What's the word for it? These over here get acidified into carbonic acid, but then breaks down into CO2 and water. And so you see the CO2 come bubbling out. Basic solutions won't do that. And acids would produce hydrogen gas from active metals. So for example, you can dissolve aluminum with hydrochloric acid. And you end up getting the salt right here, and you give off hydrogen gas. Basic solutions won't do that. And just physically on your hand, acidic solutions just feel like water. But basic solutions feel soapy. They feel like detergents, like laundry detergent. It's really hard to get it off of your fingers. And finally, just the pH differences. Okay. So we'll look at 3 definitions of acids and bases. And the first one was the Arrhenius definition. So Savant Arrhenius in 1884 came up with the first definition. He said that acids produce hydrogen ion in water. So for example, here's hydrochloric acid going to give the hydrogen ion in the chloride ion. He said that bases produce hydroxide in water. So here's sodium hydroxide giving you sodium ion and hydroxide ion. And so Arrhenius ionization, because you go from non or molecular to ions, right? We call it ionization. He didn't use water as a participant. So here's some reactions. Here's the generalized form of an acid, the generalized form of the base that it produces. And here's acetic acid, and here's how it dissociates. Here's magnesium hydroxide, and here's how it dissociates. But now, Arrhenius' definition really wasn't adequate to describe everything. Because if you get bases like ammonia, so you take ammonia, you put it in water, and the pH meter, the pH paper, shows you that this is an alkaline solution. So you take it and you put it in water, and it's like, well, how do you make hydroxide out of this? Ammonia has no oxygen. So that was a problem. Then about 50 years later, 2 guys came along, Bronsted and Lowry, and they basically took Arrhenius' definition and added water as part of the reactant. So then they had to describe acids as something that donates H+, and bases is something that accepts an H+. So here's the acid giving an H+, and here's the base. Water now is involved in the reaction, absorbing that hydrogen ion and turning into the hydronium ion. And bases accept H plus. So here's the ammonia. It's taking hydrogen ion from water, making water act like an acid to form the ammonium ion and then the hydroxide ion. So a couple of things. Notice that we're talking about the hydronium ion and the hydronium ion and the hydrogen ion. We use those almost interchangeably. And pure water is neutral because it has 1 part acid and 1 part base. And here we have water acting as a base in the front of the acid, and then it's acting like an acid in the presence of the base. So what is it? Water is both a weak acid and a weak base. And if you look at its formula, well, here's how it can act as a base, here's how it can act as an acid. So here's using the Lowry-Bronsted definition in a couple different reactions, right? And now we have a problem. And I think things like these are real problems for student understanding. Apparently, other people don't believe so. They just, oh, you just memorize that. But look at how they do the sodium hydroxide right here. Where's the water? And so if you try to use water, look what happens. With sodium hydroxide plus the water, you get the sodium ion, you get the hydroxide ion, and you get the water. We're like, wait a minute. Just like any algebra equation, you can subtract what's on both sides if they're the same, right? Water cancels out, and we're right back to this again. So some people would say that, well, when it comes to hydroxides, we have to use the Arrhenius definition. And what I'm telling you is that that's not exactly true. It's just that if you try to use the Bronsted-Lowry definition, water cancels out, so we don't need it there. Then, Lewis definition. I have this in a red box because we're not going to use it. So Gilbert Lewis was an American, and I think there was a lot of jealousy of Americans back at this time. Yeah, but if you look at Arrhenius, 1884, Bronsted-Lowry, 1923. So Lewis was before Bronsted and Lowry. And his definition is the most useful because it's not limited to just H plus and OH minus. So the Lewis definition basically gets ignored until we get to the study of organic chemistry. Then it appears all over the place. All reaction mechanisms are really using the Lewis definition of acids and bases. So, what did Lewis say? An acid accepts an electron pair and the base donates an electron pair. So what Lewis did, he went the same way as with redox reactions. Remember we were talking about redox reactions? Something loses its electrons. The electrons have to go somewhere. So everything was based upon the electrons, and that's what Lewis did. He's the same guy who did Lewis electron dot formulas. So let's look at this reaction right here. Here's the acid, here's the base, right? So these are the same things that we did up above in the other definitions. But he's saying that it's the electrons that start the reaction, it's not the H plus. So here, the partial negative from this electron cloud attacks the partial positive of that hydrogen ion. So this hydrogen ion then becomes part of the hydronium ion. Okay. So hopefully you see the difference and it makes sense to you. And what you need to understand is that an acid is an acid, no matter what definition. A base is a base, no matter what definition. The thing about the Lewis structure is, the Lewis definition is that you don't even have to have an H plus or an OH minus involved, and it still works. So questions so far? Okay, so after a couple of years of teaching, I started to notice something on the final exam. I would ask students to complete the reaction or whatever, and what I found out is that they knew a bunch of stuff about pH and all this stuff, but they didn't know the most basic thing. The most basic thing is what we've been doing all along, all the way up here with all these definitions. How do you write the reaction for an acid and water? So just to review things, the acid is going to have a hydrogen in front of the formula, right? Like in acetic acid. So this is acidic, those three are not. So because this is an acid, water will then have to act as a base. Then what do acids do? They donate H plus and bases accept them. So I see this hydrogen is going from here to here. Now if I take an H plus off of here, then I get the OH minus over here, and the H plus goes on to water. That's how I get the hydronium ion. Okay. So it's really important that you know how to write the ionization of acids and water, okay, because that's what we're going to be doing. So later on, you'll see this. The entire reaction over here, if there's a two-directional arrow, if it goes to equilibrium, the equilibrium constant is called the Ka. Okay, we'll see this in a minute. If I take the negative log of that Ka, I get what's called pKa. This also gives me the H plus. I turn the H plus into the pH by taking the negative log of it. So that gives me the pH. Then later on, if I got the pH or I have this, I can calculate two other things. The pOH and the OH concentration. And we'll look at those. That's called, well, I call it the square of death. So in order to do this, we have to be able to write the reaction for an acid and water. Then we have polyprotic acids. So polyprotic acids will not lose all of their acidic hydrogens in water. Essentially, they lose only one. So here's what happens. Even though there's 3 hydrogens that could act acidic in this molecule, if I put it in water, only one of them comes off. So here's an example. Phosphoric acid has 3 hydrogens. So some would say, oh, it's a polyprotic acid or a triprotic acid. If I put it in water, only one of them comes off. The reason is water is a very, very weak base. Now, what if I put it in the presence of a strong base like sodium hydroxide? Now, I'm going to force all of those acidic hydrogens that come off because the hydroxide is such a strong base. And what this reaction is, where it goes to completion like this, is a titration problem. That's a neutralization equation, a titration problem. So this is not a titration because the reaction doesn't go all the way to completion. You mix it together, you wait until nothing more is happening, you'll see you got some of this, some of this, some of this, and some of this. But over here, you put them together and you have none of this left over. It's all 100% in this form. And that's a titration. Then polyprotic acids cause another problem. So let's say I have this, and somebody says, take this and put it in water. Do I treat it like an acid or do I treat it like a base? Because it can act as either. So here it's acting as an acid. Here it's acting as a base. So here's something that faculty don't quite understand, that this is a point of confusion for the students. How would you know that? How would you know what to do? Treat it as an acid or a base? Well, you have to have like years of experience, and then it just becomes natural. But you guys don't have years of experience. So what I'll do is I'll tell you to treat it either as an acid or a base, just to make it less confusing. Okay, well, anyway, let's get another look at why acids are acidic. In other words, why are acids reactive, not stable? So here's acetic acid. When we write it like this, you see that red hydrogen is acidic, the green ones are not. Now look at this Lewis structure over here. Here's the green ones that are not acidic. Let's think about why are they not acidic, which means that why are they not reactive? Well, the difference of electronegativity is only about 0.35. That's a non-polar covalent bond. That means that these electrons right here forming the bond are shared fairly equally. That means that this hydrogen is pretty happy. So is that carbon. They're all happy, so why would they be reactive? Now, if I look at this red hydrogen, the one that's out in front, it's reactive, it's acidic. Why? Because this hydrogen is bonded to a very electronegative oxygen. These electrons right here are not shared equally. So hydrogen has one electron of its own, and it tried to share an electron with the oxygen to try to become 1s2, like helium, to become stable. But what it finds instead is that oxygen is pulling its electron away, leaving a partial charge, positive charge on the hydrogen and a partial negative on that oxygen. And to make it even worse, there's another oxygen over here. So it's pulling electrons this way, away from the carbon, leaving a partial positive, which then starts to pull that partial negative, or these electrons over this way a little bit more. And then that takes a little bit more from here, making this a rather larger partial positive charge. Point being is that now that red hydrogen is not happy. What does it want? 2 electrons to call its own. That's all it wants. So now it's in an aqueous solution. There's water molecules everywhere. So every time it turns around, it's bumping into a water molecule. And look at the water molecule. It's got that non-binding electron pair. There's 2 electrons that the oxygen isn't even using. Well, those electrons could be mine. So it leaves, as the hydrogen ion, it leaves its electrons behind. So you see these 2 red electrons in that bond? They're stuck over here now. That's why this gets 1 negative charge right here. So the H plus jumps over here and forms a bond with these non-binding electron pairs. So here's the new bond. And the hydronium ion now has 1 proton more than does electrons. Then, what we learned about resonance, which I know was kind of an esoteric concept. So I'm looking at this little structure right here, and I'm thinking, this is probably more stable than this. But what is the most obviously unstable part of this molecule? It's that full -1 charge on that one oxygen atom. If I could diminish the magnitude of that -1 charge, I would make that a more stable molecule. And this is one of the things that resonance does. It shows us that that's possible. So say I take this electron pair, swing it down into a double bond over here. Then I take this electron pair and swing it back up on here, because carbon can't have 5 bonds. When I do that, I get this other resonance structure. And notice that the -1 is on this oxygen, and now it's on this oxygen. And what did we say about Lewis structures? They don't really exist in the way that we think. What it means is that this bond right here has some double bond character and some single bond character, and same with this one right here. In fact, these two bonds are the same. So what we really do with resonance structures is spread that -1 charge across 3 different atoms instead of being localized on one atom. So that really makes the acetate ion more stable. So what we'll see oftentimes, why is this an acid? Maybe not so much simply because it wants to get rid of that hydrogen, but also because once it does, there's resonance stabilization, because you can draw different resonance structures. Okay. So anybody have any questions so far?
No.
Okay. I know that's kind of an interesting explanation, but yeah. What you got there in that explanation is a result of years of teaching general chemistry and organic chemistry. So I'm combining all the information about organic chemistry, which you don't normally get at this level of a course, but I think it's important that you understand what you could think of as the psychology of why these things do what they do. So then we have to name acids. So there's 3 major styles of naming based upon really what the anion is. So if they're from a monoatomic ion, and the very few polyatomic ions that don't have oxygen, our role model, our example could be hydrochloric acid, because everybody seems to know hydrochloric acid. So the root is the chloride ion, right? That's the root of this word. So we put hydro in front, and then we make it end in ic acid. So if I look at this one, there's hydro, sulfur, and then ic acid, hydroselenic acid, and hydrocyanic acid, because this doesn't have any oxygen in it, even though that is a polyatomic ion. Then the other is from polyatomic ions that do have oxygen. So these are often called the oxyacids. So here we have to go by how the name of the polyatomic ion inside of the acid is named. So you see this one? That's sulfite. This one is sulfate. So notice if it ends in ITE, it becomes us acid. If it ends in ATE, it becomes ic acid. So sulfurous acid, sulfuric acid, nitrous acid, nitric acid, phosphorus acid, and phosphoric acid. Aren't you glad you memorized those polyatomic ions? I've thought many, many times, how do I make it so they don't have to memorize the polyatomic ions? When it comes down to it, they're just so in chemistry everywhere, you really can't get around it. You have to memorize some things. And then, in this class, we won't be using the organic names. If you take the next semester, Biochem 341 at Manoa or 244 at KCC, then we'll learn how to name it with organic names. So with organic names, if you got one carbon in a row, that represents methane. So this has one carbon in a row, and it's an acid, so the name is methanoic acid. If you got two carbons in a row, that would be ethane, but the acid form we called ethanoic acid. 3 in a row would be propanoic acid. 4 in a row would be butanoic acid. 10 in a row would be decanoic acid. So it's a system based upon organic naming. The old-fashioned or common name for this is formic acid, based upon red ant bites. The red ants inject formic acid and it really hurts. And the common name for ethanoic acid is acetic acid. Okay. The naming bases, you really already know how to do this from chapter 9. So here's copper 1 hydroxide, copper 2 hydroxide. Got it? We did that already. Okay. So here's a new concept. We've talked about equilibrium several times. And the way I explained it was this: if you got 20 people in a room, and every minute one person goes out but another person comes in, you got 20 people in the room. Nothing seems to change because the rate of going in is equal to the rate of going out. And that's equilibrium. So the same thing here with a chemical reaction. So say I take A and B and I mix them together and it goes to form some C and some D. But notice this is a two-directional arrow. C and D can reform A and B. So what you get is equilibrium when the rate of A and B going that way is equal to the rate of C and D going that way. And that's the point of equilibrium. So at that point of equilibrium, the concentrations of those don't change anymore. So the equilibrium constant is the product concentrations divided by the reactant concentrations. So if I actually measure the concentration of C and D and A and B, and I put all these in here and I multiply that way, divide that way, I get a constant. And that constant can tell us a lot of information. So just briefly, what if I let this go to equilibrium and most of what I have at equilibrium is made up of C and D, so these numbers are big and these numbers are going to be small. These numbers will be big, those numbers will be small. What does that say about the constant? Constant will be a big number. So when we see a big number for the equilibrium constant, we know that it forms a lot of products. Then there's also some confusion about different ways to describe or designate equilibrium constant. And we always use a capital K for equilibrium constant. Always. A lower k means something else. Those are rate constants. Equilibrium constant is always given a capital K. And people get confused because sometimes they put little superscripts and subscripts on here. They decorate it with different things. But I'm looking at all these different ways, all these different designations, and they're all equilibrium constants because of the capital K. And what do? You take the products and divide by the reactants, and you get a number. That's it. So we have two ways to write equilibria. Almost always we use homogeneous equilibrium. Heterogeneous equilibrium can contain more than one phase, but homogeneous is only one phase. So in reality, we use most of the time homogeneous equilibria in water. And in homogeneous equilibrium, we treat pure liquids and constants as if they were equal to 1. We forget about them. And I remember having an argument with one of my chemistry teachers, who actually, I used to play music with his son. It's kind of interesting, but I told him we're not omitting anything. We're just saying it equal to 1. So why do we leave out water? Well, because it's a pure liquid, and because its concentration is very high, and it's not going to change very much if you add something to the water. Here's a way to calculate the concentration of water from its density. It's about 1 gram per mil, so about 1,000 grams per 1,000 mils. Then, if I take grams and I convert it into moles using the molar mass of water, I get 55.5 moles per liter in pure water. That's a huge number. And if I add a little bit of something, I'm not going to change that number. So let's look at this reaction. Here's the products on top. Here's the reactants underneath. I'm going to leave out the water because it's the solvent, and it's a huge number. If these are just small numbers and I put 55.5 in there, the value for Ka is going to be dominated by 55.5. So in general, in homogeneous equilibria, we only care about the solids that are dissolved in the solution. So remember this about saturated solutions. If I got water and I keep adding HA, in the beginning, this is all going to dissolve and everything, but then if I get past the point of saturation, what happens? The acid will just go to the bottom. It doesn't matter how much is down at the bottom. If this is a speck or if it's 1,000 grams, this will simply be a saturated solution, no greater. So this would be variable when we don't want a variable in there, we want a constant. So when we dissolve an acid into water, it shows its ionization. So here's carbonic acid. So it's a diprotic acid, but I put it in water. How many hydrogens do I take off? 1. So I get bicarbonate or hydrogen carbonate and the hydronium ion. So then I take the product concentrations, divide by the reactant concentrations. I leave out water, and here's the expression right here. And why is it called Ka now instead of just K? A stands for acid. The capital K means it's simply an equilibrium constant. And bases are treated the same way. So here's the base, here's the acid. Now notice that this right here could either act as an acid or a base. But the situation I'm explaining to you to treat it like it's a base. Okay. So what do bases do? They accept hydrogens from the acid. So nevertheless, here's our products, right? And our reactants, and I left out water. And I put KB here because B stands for base. So here's one for lactic acid. Okay. Here's one for lactate. Okay. Make sense? Okay. So now we'll put some numbers in here. If we made a 1 molar solution of lactic acid, and then we measured the concentrations of everything at equilibrium, here's what we're going to get. I started weighing out enough to make 1 mole per liter. I put it in water. As soon as, when I was doing that, there was none of this and there was none of this, right? Then if I measure at equilibrium, the concentration of lactic acid is not 1 anymore, it's 0.9883 moles per liter. So what happened to that missing 0.0117? Well, stoichiometry tells you what happens. One of these makes one of those. 0.0117 of those makes 0.0117 of those. Every time I make one of those, I also make one of those. So these concentrations are the same. So now I have all the values at equilibrium. So equilibrium constant is products over reactants. Leave out water because notice it didn't even change. So that's 0.0117, so is that. So notice I just combined it, made it squared, and this is 0.9883. So these are the concentrations at equilibrium. So I crunch these numbers and I get this value. 1.38 times 10 to the minus 4. So is that a big number or a small number? It's a small number. This number tells us what we just saw over here. When you put this acid in water, you don't make very much products. That's what that number means. This is the same as this over 1. So if I divide 1.38 times 10 to the minus 4 by itself and then divide this by 1, I get this. What that really means is that for every 1 product that you form, you have 7,000 something reactants left over. This small number right here means that the reaction didn't go very far. It means that lactic acid is a pretty weak acid. By the way, lactic acid is the same acid that you make in your body, right? Lactic acid. So a large Ka indicates that there's a lot of products compared to reactants. So here's another way to assess that. Besides using the Ka, we can also use the pKa. So what is the pKa? Well, it means the negative log of the Ka. So the P stands for the negative log of a number. Pretty soon we'll look at pH, but just so happens I think it's more logical to teach pKa before we get to pH. So now your calculators are probably going to be different. Here's the major way that you do it on a calculator. Sometimes you'll have to push the change sign button, then you hit the log button. Then you input your KA, and then you hit the equal sign. In other calculators, the logic is you input the KA, hit the log, and then you change the sign. And I have no idea what your calculator would be like, so you just have to figure out on your own which is the one that your calculator uses. So note that the log of 10 to the 0 is equal to 1, because 10 to the 0 is 1, right? So the log of 1 is 0. The log of 10 is 1. The log of 10 to the 2 is 2. The log of 10 to the minus 2 is minus 2. This is the reason why we put the negative over here to turn this into a positive number. So here's the pKa, here's the Ka for lactic acid, and here's the pKa, what we do with it. So I put it step by step. When we take the logarithm, you're doing the logarithm of the 1.38, and you're doing the logarithm of 10 to the minus 4th. But notice I'm taking the negative logs, right? So I get this value and I get that, so it turns out to be 3.86. So what you need to be able to do is simply put in this number right there and get 3.860. So a couple of interesting things. If you look at this value for KEQ, there's 3 significant figures in it. If you look at the value for the pKa, that also has 3 significant figures in it. The reason is the first number, 3, came from the power of 10. Okay. So what that means is the power of 10 right here, plus you got another part of it has 3 significant figures. Then one more thing, we're using log of base 10. Don't use the natural log. Usually the natural log is ln, log to the base 10 is log. So give the pKa for lactic acid. If that's its Ka, you should get the 3.860. Give the pKa for acetic acid. Here's its Ka. So I take the negative log of that, I should get 4.750. So let's see what that means. I'm asking the question, is acetic acid stronger or weaker than lactic acid? If you look at the Ka, here's a bigger number than this, right? So based on the Ka, you're going to get more products from lactic acid. Lactic acid is a stronger acid. What about the pKa? Oh, it's a bigger number. So what that means is a stronger acid will have a larger Ka, but a smaller pKa. And likewise, a stronger base will have a larger Kb and a smaller pKb. So the lactic acid that you produce in your body from anaerobic exercise is actually stronger than what's in vinegar. The vinegar is about a 5 to 8% solution of acetic acid. So lactic acid is responsible for sour milk produced by your muscle cells. And fishermen of which I used to be a fisherman a long time ago. Well, maybe I still am. We always go into the Papio tournament in Waimanalo. But sometimes fish will fight so hard that they die from acidosis. That means that their body fluids, their blood gets so acidic and they produce so much lactic acid that it actually will destroy the flesh of the fish. So that happens with, especially with marlin. So when you catch a marlin, you see that marlin dancing all around like that. It's trying to throw the hook, right? If you watch it on TV, they bring the marlin close to the boat. That marlin is not fighting anymore because it's almost dead. So what they have to do if there's catch and release is they have to take the hook out and pull it through the water, get air over its gills, and let it be able to finally get rid of all that lactic acid so it can actually be alive again. And oftentimes when you catch a marlin, it doesn't jump up in the air and fly around. It simply dives deep, trying to escape from whatever is happening to it. And usually by the time you get one of those to the boat, it's dead already. And the meat is not very good sometimes because it was destroyed by all that acidic lactic acid. I took one of my peacenik vegetarian friends fishing one time and we caught some fish. I forget what it was. I think it was an Ono. And he's like trying to get us to throw it back because that Ono didn't want to get caught and died. And I'm like, yeah, that Ono is a mass murderer, killing all kinds of other fish. Interesting. So questions so far? I know it's a lot. So let's just put this all together into this problem. So we made a 1 molar solution of sodium hydrogen carbonate. And I'm telling you that hydrogen carbonate is a weak base. So that means you're going to treat it like a base, right? So here's the concentrations at equilibrium. So in other words, somebody made a 1 molar solution of this, stirred it up, waited for a while, and then they measured the concentrations of all these things. So these were 0 at the beginning. Now at equilibrium, this is 0.999 something. This is the rest of it. That's this number right here, right? So to calculate the equilibrium constant, it's simply products over reactants. Here's the value for the products and the reactants. I crunch the numbers and I get this number. And if I take the negative log of this number, I get 7.6. Okay. So I'm pretty sure you guys can do that. By the way, is this a strong base or a weak base? (10 to the -8th is an incredibly small number, isn't it? So that means that this reaction doesn't go very far. And look at the numbers up here that reflect that. I made a 1 molar solution, but not very much of it went form products. It's a weak base. So this part in the red box right here, you're not going to have to do this. If you take Chemistry 162, they'll make you do this because those people are just mean. But I just want to show it to you. What if we had the value for the Ka? What use is that to a chemist? Well, without having to do the experiment, because this experiment was already done and it was documented, right? Say I make a 1 molar solution of this acid. Here's what it would do. So this would be 1 molar in the beginning, that would be 0. Then it's become 1 minus something. I don't know what x is, but x went that way. By the stoichiometry, every time 1x goes that way, I make x of these and I make x of those. So the Ka would be product concentrations over reactant concentrations, and I have values for those. X times x, and this would be 1 minus x. And that is equal to this number right here. So all I have to do now is solve for x, and I'll figure out what these concentrations are. So I put it into the quadratic equation form, and when I solve for it, I get x is this value right here. Okay. I'm sure you guys remember all this from school, right? Quadratic equation. So let's just put this in here and to check it. So here's, where are we? Here's 1 minus x over here. Here's x and here's x. Now if I put it back into the reaction equilibrium constant, then what do I get? Oh, the same value. So yes, it works, doesn't it? So here's the kind of thing that numbers are good for. So I have a list here of acids with their Kas and pKas. The strongest acid would be what? One with the largest Ka, which would be E, or the smallest pKa, which is also going to be E. The weakest acid will be one with the largest Ka. Okay. I'm sorry, I said that wrong. With the smallest Ka and the largest pKa. So which two acids are closest in strength? Here's a 10 to the minus 5 and a 10 to the minus 5. Yeah, so A and D. Which acid has the largest percent dissociation and percent ionization? That would be the strongest acid, right? Which would be E. Similar to that. Well, I hope you guys catch on to that. So now, what about strong and weak acids? Strong acids are considered to be 100% ionized, 100% dissociated, and we use a single directional arrow to indicate an irreversible reaction. Okay? Like here's a list of strong acids. Notice that I'm all using one directional arrows right there. So as it turns out, that's not exactly true. More precisely, what it means is that the Ka would be very large and the pKa extremely small, because this concentration cannot be 0 because we're not allowed to divide by 0. Did you guys ever do that on your calculator? Just put in a number, then try to divide by 0 and hit the equals sign? I mean, does Homeland Security show up and arrest you, or you get interrogated, or you're never seen again? Your family will miss you forever, never know what happens, never closure? No, it just says error, right? So let's just look at it in terms of limits. So here's an acid and water. So products over reactants, right? Now, I'm not allowed to divide by 0, so HA cannot be 0. But what happens when HA gets extremely small? The smaller this number is, the bigger the Ka gets. So Ka approaches positive infinity. What about pKa? The bigger and bigger the Ka gets, the smaller and smaller the pKa gets. So pKa starts to approach negative infinity. So there's many reasons why I decided to write my own book, and never did capitalize on it or anything. But I just couldn't figure out a lot of reasons why textbooks did certain things. One of them is they want you to memorize a list of strong acids, then memorize a list of moderately strong acids, and memorize a list of weak acids. So memorize, memorize, memorize. But I don't want you to have to memorize. I would rather have you understand stuff. So what I did is that we're going to have only 2 categories of acids: the strong acids and then everything else. Everything else we'll treat like a weak acid because, as it turns out, moderately strong acids are treated the same way as a weak acid. So de facto, there's really only 2 categories. So what you need to do is memorize this list of 7 strong acids. Now, if you come across an acid that is not on this list, how do you treat it? Like a weak acid. So a lot of these you kind of know already. The first one is Hawaii. Oh, no, that's hydroiodic acid. And then hydrobromic acid. And then I put them in order of decreasing strengths. And this one is called perchloric acid. This is not only a strong acid, but it's also a strong oxidizing agent. It's a very dangerous substance. I think I don't have any more in the lab. I think I got rid of it. Then hydrochloric acid. So that one you know, that one you can't forget. Sulfuric acid is one, and then the hydronium ion is one. So most textbooks, I wouldn't say that most, I saw many textbooks will try to make a simplification. A strong acid is anything that's stronger than hydronium ion itself. And when I really studied this, I found that, well, nitric acid is always on the list, but nitric acid is actually a little bit weaker than hydronium ion itself. Not much, a little bit. So notice that these pKa's are huge. The Ka's are huge, and the pKa's are negative numbers, because these are extremely strong acids. They essentially go 100% to form product. But when you look at the numbers, some interesting things show up. Notice that hydroiodic is orders of magnitude stronger than most of these other ones. Way stronger. Factor of 1,000. Okay. So you're going to have to memorize those 7 strong acids. What about weak acids? Weak acids are those that are not close to 100%, and we simply use a 2-directional arrow. In other words, they go to equilibrium, and these guys don't. So notice what we do. This was not on your list of strong acids, so I'm telling you that it's an acid. So the H plus goes from here to here, but it's a two directional arrow. Here's HF, hydrofluoric acid. Notice that over here we got iodine, bromine, chlorine, but there's no fluorine. Fluorine gives you a weak acid. So a couple of things. One directional arrow, two directional arrow. Huge Ka, smaller Kas. Extremely small pKa's, not small pKa's. Okay. So weak acids can still be dangerous. So what is it that makes a solution acidic? It's the concentration of the hydrogen ion. So you can get a particular concentration of hydrogen ion using a little bit of a strong acid or a lot of a weak acid. So never underestimate the danger of a weak acid. So a strong acid really wants to get rid of its H plus, and when it does, it won't take it back. A weak acid kind of wants to get rid of its H plus, and when it does, it kind of wants to take it back. So what is the concentration of hydronium ion in a 3 molar solution of an acid if there's 75% ionization? Okay, well, if this were completely ionized, and this is 3 moles per liter, then I would get 3 moles per liter of the hydronium ion. But I'm getting only 75% of that, so that gives me 2.25 moles per liter. So when 0.5 moles of acid was dissolved in 2 liters, hydronium ion concentration was determined to be 0.111. Is it a weak acid or strong acid? Okay, well, let's see. I'm writing this equation in water so I can get an idea of how to answer the question. And then I got 0.5 moles of the acid in 2 liters, so that's 0.25 moles per liter of the acid. Complete ionization would give me 0.25 moles per liter of hydronium ion. But I'm only getting 0.111 out of a possible 0.25, so that's about 44% ionization. So that's a weak acid. Okay. So the next one's kind of self-explanatory. So you guys will ask questions if you have questions, right? Yeah. So let's look at bases for a minute. Strong bases and weak bases. So a strong base contains hydroxide in the formula, regardless of its solubility in water. And we will use a one-directional arrow to indicate an irreversible reaction. So here's some strong bases, right? So now I've made a simplification. And I don't know whether it's a simplification or whether it's just applying common sense, but technically, strong bases must also be soluble in water to produce large amounts of hydroxide ion. So if you had a base that wasn't soluble in water, it wouldn't make a lot of hydroxide ion. But that's not the total definition of a base. A base is also something that accepts a hydrogen ion from an acid. So what if you reach the saturation point? You got a whole bunch of, say, aluminum hydroxide on the bottom of the solution, and you start adding some acid to it. What's going to happen? You'll use up the hydroxide that's dissolved, and what will replace it? More aluminum hydroxide in the solid will redissolve to try to handle more of the acid. It will do that acting like a strong base. So I don't want to mix up solubility rules with what is the definition of a strong base, that's all. So for you, a simplification is you see hydroxide in the formula, hey, strong base. So what would a weak base look like? A weak base would be ammonia. Ammonia is NH3, and the only way it makes hydroxide is by hydrolyzing water, making water to act like an acid. Okay, so it's a reversible reaction, right? Where these one directional. Okay. Then ammonia has some organic counterparts, organic analogs. They're called amines. So in organic chemistry, amines are the naturally occurring bases. In biochemistry, they're the bases. So what I did here is I took off this one hydrogen and replaced it with a methyl group. So this is now called methylamine, sometimes methanamine. So why is it acting like a base? Well, ammonia acts like a base because it has this non-binding electron pair on the nitrogen. And that attracts the H plus in a water molecule. Not strongly, but it does. Notice that with methylamine, that is still there. The thing that makes ammonia a base is still there in methylamine. It's also there in ethylamine. It's there with all the amines, therefore all the amines are bases. So you do the same thing as you do with ammonia. The H plus goes from water to the nitrogen, and you form the salt. Okay. So let's revisit water again. So we consider it a very weak acid, at the same time a very weak base. So adding acid to water makes water act like a base. Adding base to water makes it act like an acid. So whether a molecule is considered an acid or a base is really kind of a relative thing. So most people would not consider ethanol to be an acid or a base. But I can do it. I could do it right here in this lab. All I need is a really, really strong base, such as the amide ion. So I can generate amide ion using, say, lithium and things like that. And now what does this do? It wants to form ammonia. Oh wait, ammonia is a base. Why is it a base? Because it wants a hydrogen ion. But the amide is an extremely strong base. So even though we don't consider ethanol as an acid, this will extract that hydrogen from it, making the weaker, more stable base ammonia. And then I make what's called the ethoxide ion. So this was a very weak acid, so this is going to be a very strong base. Now I can take this ethoxide and take hydrogen almost off of anything. That's how strong it is. So my point here is that whether something's an acid or whether something is a base really depends upon what it's in the solution with. So we'll stop there for today. So does anybody have any questions about anything? Life, viruses, cars, dogs, boyfriends. I got a PhD, I can talk about anything. No questions at all?
I had a question on the homework actually. Homework 19.
Huh?
Chapter 16. Homework 19, chapter 16.
Homework 19. Oh, yeah. Go ahead, I'll pull it up.
It was on number 8. I don't understand the first question in number 8.
The boiling point of ethanol?
No, it was the kinetic theory question.
Homework. Oh, that can't be homework 19. Is it homework 19?
Yeah, it says like if molecule A has a molar
Oh,
mass.
number 9. Okay. So if molecule A has a molar mass of 30 and molecule B has a molar mass of 50, and the two molecules have equal intermolecular attraction, which molecule will have the greater velocity? So by going to the equation above, the kinetic theory equation, so they're at the same temperature, right? So temperature is the same, kinetic energy is the same, 1/2 is the same. So now, if mass times velocity squared is going to be the same, that means if you have a big mass, the velocity has to be smaller. That makes sense?
Yes. Okay,
The
yeah.
larger the mass, the smaller they're going, the slower they're going.
Mm-hmm.
The slower they're going, the harder it is to be breaking away from attractive forces because they're going slow.
Oh, okay.
Yeah?
Okay, that makes sense.
Okay. That's all? So easy. If you guys have other questions, you can always email me or post on, discussions and private messages. And, I check this stuff all the time. Well, except when I'm sleeping. But then when I'm sleeping, I dream about checking the email and stuff. So, yeah. Okay, well, I guess I'll end the meeting and then I'll get this up on the YouTube channel pretty quick. Takes about maybe an hour. Sometimes it takes longer. It's just processing by Zoom and then by YouTube. Okay? So stay safe out there. Have a great evening.
Thank you.
Thank you. Okay, bye.
Bye, thank you.